Alright, so let's start our discussion tonight with the notion of acceleration. Actually, we all know what acceleration is. It's the rate at which velocity changes with respect to time. Or in other words, acceleration is the derivative of velocity with respect to time. So, if the position of an object at time t is s and s is a function of t, then its acceleration at that same time instant t is dv dt, derivative of velocity with respect to time, and we denote acceleration by a of t. Now we know from our previous discussions that velocity itself is the derivative of position with respect to time, and that's why acceleration becomes the second derivative of position with respect to time, d squared s dt squared. Now in general, acceleration is a function of time because at different instants of time during the motion of a body, it can have different acceleration values. However, you may remember that in the beginning of chapter 1, the authors mentioned that near the surface of Earth, all objects fall with the same constant acceleration. Now, in the absence of air resistance, or say air is there but air resistance is negligible, if the only force acting on a falling body is the force of gravity, then the way the body falls is called free fall. We have actually already used this term and discussed free fall a little bit previously. Now, the mathematical description of this type of motion interested many great thinkers like Newton, Galileo, Aristotle. It turns out through experiments and theoretical investigation that when an object is falling freely, when it is having free fall, then the distance it falls in time t is directly proportional to t squared, the square of time. If you express this mathematically, you get this equation. S is the distance the object falls in time t, that is proportional to t squared, and if you write that as an equation, it looks like this: S equals 1 over 2 times gt squared, where S is the distance the body falls in time t, and g is the acceleration due to Earth's gravity. I mean, we are talking about free fall near the surface of Earth. A similar situation is also there for every planet, every celestial object. Now, this you should understand that this is an ideal equation. Ideal equation in the sense that it only works in vacuum where there is no air, because you won't really get such a situation in real life. I mean, you can get, but not on Earth. You can artificially get, you won't get naturally, but you can arrange for an artificial situation where there is no air, Say you create a vacuum in a closed chamber. So there you can have this equation exactly modeling the free fall of objects. But still, for some dense and heavy objects like rocks, ball bearings, the first few seconds of their fall indeed is free fall, and that can be modeled with great accuracy by this equation, even if their motion really not exactly free fall. During the first few seconds it remains free fall because there the speed is not that much. But as the speed increases, air resistance starts to pick up, and so it no longer is negligible. Now, the value of this constant, which we also know as the acceleration due to gravity, are these in 2 units. And in fact, based on these values, we have the free fall equation in 2 different systems of units. For our planet. First we have English units, in which the value of G is 32 feet per second squared, and based on this value the free fall equation looks like this: 16 t square feet. In fact, when we discussed free fall previously, you may remember that this is what we used in one example. However, if we use metric unit, which is the more popular and scientific one can use English units, there is no problem, but the conversions are really cumbersome, whereas in metric units it's really neat, multiples of 10. In metric units, the value of G is about 9.8 meter per second squared, and now the free fall equation takes this form: 4.9 meter per, what am I writing? It is distance, meter. Yeah. Alright, now we are going to discuss these things in 2 examples. So let us see this next example first. A ball bearing, let me just simply write ball, is falling freely due to gravity near the surface of Earth. Part A asks, how many meters does the ball fall? In the first 2 seconds. There is a part B also, but let us answer this first. Actually, there is a diagram also. If you want, I can, let me draw the diagram. I won't make it very accurate and we don't need to actually. The diagram is just roughly this. I just want to show something about the diagram, that's why I am drawing it. So you have points here, 5, 10, 15, 20, 25, 30, 35, 40, 45. Okay, so these are the heights in meter, S in meters, which increases downwards because the object is falling and its distance from the point where it started its fall is increasing with time, and time is measured in seconds. So here you have the object. So at this instance of time, if I am remembering the diagram correctly from the book, at t equal to 0, of course, the object is at that height. At t equal to 1, it is roughly here. At t equal to 2, it's here. At t equal to 3, it's here. And t is measured in seconds. So what I wanted to draw your attention to is the fact that here you are looking at an s-axis. Do you remember that when we were discussing in the previous video, or I think the one before that, that along the s-axis, a coordinate line, something is moving. So that coordinate line is this one here, and the downward direction of the s-axis is the direction in which its values are increasing. That means it's the positive s-axis. However, while having that discussion back then, we drew the s-axis like this and defined velocity and speed like this. The point here is that it's up to you to decide what you want to take as your s-axis, and also which direction of s-axis you want to consider as the positive direction. It depends on you. You have the liberty to choose your coordinate system. This is a great convenience because our motion now is downward. It's convenient for us to choose this as the s-axis, a vertical axis, and that to one which is positive downwards. This is not how we generally draw axis in coordinate geometry, but it can be done. One can actually consider the downward direction as the positive y-axis and the upward as the negative y-axis by rotating axis. Such things are possible and necessary even, because you can see one instance where this is necessary. Okay, so that's why primarily I wanted to show the diagram. So this is how the ball is falling. Okay. So now we have to find how many meters the ball falls in the first 2 seconds. But you may suddenly think we do not have any equation, but we have, because it's free fall, it's assumed to be free fall. So we can use the free fall equation, that's it. And that too, because S is measured in meters, so that's why we have to use the metric free fall equation. If you use that, what is the equation? The equation is this meter. So that means you have to calculate S of 2. S of 2 will be how much? 4.9 times 4. 19.6 meter. This the body will fall in the first 2 seconds of its motion, of its fall. And now let us see part B. What are its velocity, speed and acceleration then? That means at that instant of time. Okay, so just use this equation. First we find velocity and acceleration at a general time instant t, and then we will substitute t equal to 2. So velocity is the time rate of change of position. So if you differentiate this using power rule, this 2 will come down, will get multiplied with 4.9 and we will have 9.8, and t squared will become t because the exponent gets reduced by 1 and the unit of course is meter per second. And then to get acceleration, you differentiate once more with respect to time. So differentiating this with respect to t, of course, is going to give you 9.8 meter per second squared. So you see that indeed the acceleration is constant, although it's a function of time, but it's a constant function of time. At every instant of time it is having only this value. So in particular, the velocity when t is 2 seconds is going to be 9.8 times 2, that is 19.6 meter per second, and acceleration when t is 2 is just 9.8 meter per second square. Now a little comment about the notation we are using. You see that sometimes I am writing s, sometimes I am writing s of t with some specific value of t. They mean the same thing, okay, namely that the position s is a function of time. It may become confusing because normally when we write function, we sometimes use the same letter to denote the output value s, for example, and the function name. Here s itself is considered as the name of the function, as well as s is considered as the output or the dependent variable. This is a common practice. So sometimes we simply write s to make things look simple, but if you have to evaluate that at some point, we may as well very well write s of something. Okay. So similarly, we have these functions of time as well, v and a. Velocity and acceleration also both are in general functions of time. So they can be evaluated at some time instant, although this notation may make them look like they are constants. No. Okay, so that is our example 4. Oh, I forgot something, no? We have to find the speed as well, the speed of the ball when t is 2. Speed which in general can be negative, that's not correct. Velocity, which in general can be negative, speed is never negative. Speed is the absolute value of velocity. But here velocity itself is positive, so that itself is the speed. Okay. Next, let us see another example. Example 5. This one also involves a downward motion but an upward motion as well. In fact, it also has a diagram. Let me draw that diagram. That will clearly show, I mean, of course, we will write down the question also, but still it will show us more clearly what's going on. So what happened here is that there is a rock, okay, and there was a dynamite blast which blew the rock up, straight up. So the rock went up and reached some maximum height due to gravity, because initially it went up with the momentum gained from the blast, but gravity is pulling it downwards at every instant of time. So it gradually lost its motion, it reaches, so its speed gradually decreases, it reaches the maximum height. At that height its speed is 0 or velocity is 0, same thing. Velocity being 0 and speed being 0, they are essentially the same thing. And then immediately it started falling. So during the first half of its motion, it went up like this, but then it started to fall after reaching that maximum height. This diagram may be a little confusing. We may think that the rock went up like this and then had a slight horizontal displacement and then it came down. No, the authors drew the diagram like this just to show that we also have a part of the motion where it comes down. So they have decided to draw the downward motion alongside this motion, but it just simply goes up along this line and comes back down along that same line. You can understand. Now at this height, something has been asked. This is the height 256. This is the height 0. And this is the maximum height that the rock reaches. So it's being denoted by S max. You note one more thing, that in the previous example our S axis was positive downwards. Here however it's positive upwards. It's up to you. Here also you can choose the downward x axis as S axis as the positive S axis, but the upward direction has been chosen as the positive direction, but there is a downward half of the motion as well. And in fact, here height is measured in feet, not meter. Time is measured in seconds. So let's first write down the statement of this example. Oh, and because we are having this discussion, let me just digress for a little bit and tell you a very important thing. Suppose you are discussing about this motion of the rock with this coordinate system in which the s-axis is increasing, or it has the upward direction as a positive direction. For some reason you want to change this. For some reason, say, just out of curiosity you change the s-axis. Now say your s-axis is tilted like this, or in fact is increasing in the downward direction, say. Then whatever discussion you are having about the motion of the rod, that will change with respect to the new position of the s-axis. So your equations of motion, everything will change if the coordinate system changes. Sometimes what happens now, some physical laws do not change even when you change your coordinate system. Just keep this in mind. Okay, why they do not change, what this signifies, I am not going to say anything about this right now itself. Just remember this. At some point this is going to be important for us in future, at some point. Okay, now example 5. A dynamite blast blows a heavy rock straight up with a launch velocity. That means there is an initial velocity that the rock had from the dynamite blast. Of what is the amount, 160 feet per second, which is about 109 miles per hour. It reaches a height of this many feet after t seconds. Okay, so this is the situation. So actually this equation itself tells us everything that we need to know about this motion. Next come the questions. The first one is, how high does the rock go? What is this maximum height? Let's see the motion once more. There was a blast, it immediately went up due to the force, reached a maximum height, and then it started falling, and at some instant later it comes down and hits the ground. During this entire motion, the only time instant where the velocity is zero is this instant when it reached its maximum height. This means that in order to know what S max is, we need to know the time instant, and in order to know the time instant, we need to solve this equation for t, because v after all is going to be a function of t, but we do not have v, we have S. So, from this, after differentiating with respect to time, we are going to get v, we will solve the equation, find the value of t and use that value back in the equation of S. That will give us S max. So, let us do it. So, what is V from this? ds dt. Using all the differentiation rules, this is what we get. And if we want to write the units, feet per second. Now we solve the equation v equal to 0 for t. So, I am not writing anything systematically, okay. We are just seeing the calculation. Minus 32t is 0, or you can see that you will have t equal to 5. So, when t is 5 seconds, at that time instant, the rock will reach its maximum height. So, we now have to calculate just S of 5. So, S of 5 means here put 5 in place of t. Minus 16 times 5 square. If you do this calculation, you will see that you are getting 400. So, 400 feet is the maximum height the rock will reach. Alright. So, that is part A. Next, part B. In fact, this portion of the motion is what part B is all about. What are the velocity and speed of the rock when it is 256 feet above the ground on its way up and on its way down, both. You can clearly see that this height is reached once when going up and then again once when coming down. So, we have to find the velocities at this time instance when these two events happen. Because the height itself is given, we have to use the formula for S to solve for t in order to know the time instants when this height is reached during those two instants during the motion of the rock. That means we have to calculate or we have to solve this equation. So if we now use the formula for S, we get 160t minus 16t square is 256, which is equivalent to the equation 16t square minus 160t plus 256 equal to 0. Now luckily all these coefficients are divisible by 16. If you do the division, the equation simplifies to this: t square minus 10t plus 16 equal to 0, which is just t minus 2 times t minus 8 equal to 0. That is, either t is 2 or t is 8. So it's clear that at which instant what happens. When t is 2, the rock reaches this height while going up, on its way up, and when t is 8, because that will happen afterwards, the rock again comes back while falling down, it reaches this height. But we have to now do what? We have to find the rock's velocity and speed at these instants of time. So let's calculate v of 2. What is the v formula? The v formula is 160 minus 32 times t. So you will, if you calculate this, you will see that this is 96 feet per second. And what is, okay, so what is the speed? This is the velocity. The speed is the absolute value. So this is also 96 feet per second. And what happens when t is 8 seconds? Minus 32 times 8. This time if you do the calculation, you will see that it becomes minus 96. Not meter, feet. As we said earlier, during the motion, during the upward motion, the velocity is positive, because that's the direction in which s is increasing, but during the downward motion the velocity is negative, because in that direction s is decreasing. So that's why we have this minus sign. And the speed at this instant is also 96 feet per second. So the magnitude of these two velocities are the same, but their directions are different. Do you see? That's why velocity is a vector. Of course, we already know, but here it has become really more clear. Same magnitude, but different opposite directions, in fact. Next, part C. What is the acceleration of the rock? at any time t during its flight after the blast, of course. So we just have to calculate the general acceleration means acceleration at any general time interval, time instant t, not interval, of course. Acceleration is, I think it will be a good idea to write a of t here in order to emphasize the general nature of a. But if you want, you can of course write simply a dv dt. So what was our v? V was 160 minus 32 t. If you differentiate that with respect to t, you get minus 32 feet per second square. So here also acceleration actually ultimately does not depend on t, it is constant. So this is another situation where acceleration is constant. And finally there is one more part. When does the rock hit the ground? The rock hits the ground. You see, when does it hit the ground? This is not being asked when it is on the ground. There is a slight difference between these two things. The rock is on the ground at two instants of time. Before the explosion or rather when the explosion just started, at that instant the rock is on the ground, and then once more when it reached the ground. After that, of course, it continues to be on the ground unless it's disturbed by something else. But it hits the ground means after going up, when it comes down and then it hits the ground. So we have to find that instant of time, and at these instants s is equal to 0. Do not forget that s is not the distance. This is something which people often confuse, including me sometimes, that s is the distance that the rock has traveled. No, s is the position of the rock on the s axis. So now we have to simply solve the equation s equal to 0 for t. That means we have to solve this. Or if you take 16t common out, then you are having this. Obviously, this is not what we want, but this is what we want. So, at the 10-second mark, the rock will hit the ground. It will come down and it will hit the ground when t is 10 seconds. If one draws the velocity versus time and position versus time curves of the motion of this rock simultaneously, then one gets these graphs. the position versus time graph looks like this. So this is 160t minus 16t square. So this is where t is 0, t is 5 and t is 10. And the velocity versus time graph looks like this. This is 160 and this peak is at the level 400. You can of course understand that it's not in scale. If you really draw this graph in using a graphing facility, say Desmos graphing calculator, it becomes really high due to this 160. But just to show it clearly, the authors also in the book have drawn it like this, out of scale. And this is the velocity graph, velocity versus time. So this is a parabolic curve, but this one is a straight line, you can clearly see. In the book also this may confuse you, that simultaneously this axis is being called the v axis as well as the s axis. That's because we have drawn two different graphs in the same place. So we are simultaneously using this axis for velocity as well as position. So you can see some things from this graph, namely that when the maximum height of 400 feet is reached, that is the time instant when t is equal to 5, and that at that instant velocity is 0, because that's where the velocity graph crosses the 0 axis, v equal to 0. 0 axis means the value where v is 0, the time axis. Also, when the body was moving upwards, during that phase of the motion, the velocity values are positive, they are above the time axis. But during the other phase of the motion, when the body was coming down, velocity is negative, because all the velocity values are now below the time axis. So they are having negative values. You can see one more thing. I mean, the velocity graph you can clearly see here, but what is velocity geometrically if you think of it in terms of the position versus time graph? It is the slope of the tangent at any instant of time or at any value of t here. For example, say your time instant is this. What is the velocity at this instant? From the velocity graph you get this velocity value, but simultaneously at this instant this is the position, and if you draw the tangent to the curve at this point, something like this, that tangent has some slope, that slope is this value. The slope is positive because the tangent is tilted like this. At the instant t equal to 5, the tangent becomes horizontal. So slope is 0, there the velocity is also 0. After crossing this t equal to 5 second mark, at any further time instant, say at this time, the tangent has a negative slope because it's tilted like this, and the velocity accordingly has a negative value. Okay, in fact, the slopes are these values. Okay, so that's the significance of having these two graphs together. So let's just end the video here itself. There are one or two more things in this section. The next topic is sensitivity to change. We will see what that is in the next video. And there is a slight means a very small application of these ideas to some parts of economics. And tomorrow we as usual have our linear algebra problems. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.